Hello everybody, and welcome back to another lecture video. I hope you guys are all doing well and are excited to learn about my favorite element type, which is quadrilateral elements. So again, we covered general solid elements and we said that, well, there's a bunch of different types of these general solid elements depending on which shape functions you guys assume. And we said that in later videos, we are going to cover these different types, and today we are going to cover the quadrilateral elements. So the formulas that I present here, they were previously derived in a different video. If you guys are wondering where that video is, well, I'll have a link in the description down below. So as I was saying, now that we have expressions for both the stiffness matrix and the nodal forces vector for general solid elements, we can begin to look at some of these common element types. In this particular lecture video, we are going to look at quadrilateral elements. So recall that for general solid elements, we have the following formula for the stiffness matrix, where it's B transpose multiplied by C multiplied by B, and then integrated over the element. And we had a nodal forces vector, which is going to be N transpose times our traction vector Tn, integrated over the surface at which that traction vector acts, plus N transpose multiplied by rho B, and then integrated over the element. This is essentially counting for distributed loads, as well as factors such as gravity. But at the end of our lecture of general solid elements, we said, well, we kind of have a little bit of a problem. That B matrix that we had, as well as that N matrix, well, they depend on the element type and geometric order. So in our previous video, we actually looked at what happens when we use triangular elements, and now we are going to look at what happens when we use quadrilateral elements. So we're going to look at two types of quadrilateral elements, and the first one is a linear quadrilateral element. So one of the most distinguishing features of this element, as you guys can see, and perhaps are most familiar with, is the fact that they are basically just rectangular elements. Quadrilateral sounds really nice, but we can also just call them simple rectangular elements. Now, when we look at this particular element, a linear quadrilateral element, we can see that it has 4 nodes, one located at each of the corners of the element. Now we can extend this to a quadratic quadrilateral element. I know I'm already going to mess up saying that so many times. It's quite a tongue twister for me. And in this element, we introduce 4 additional nodes at the midspan of each of the surfaces, resulting in a total of 8 nodes. Now to begin, we're going to look at the linear quadrilateral elements because, as you guys may have guessed, the linear case is going to be more simplistic than the quadratic case, but in the end, it's always going to be the same procedure. So when we're looking at a linear quadrilateral element, we said that it's essentially just a rectangular element with nodes located at each of the corners. So for this particular type of element, it's going to have 4 nodes, and we typically number the nodes starting at the bottom left corner and then going counterclockwise. So we go 1, 2, 3, and 4, nice and easy. Now to make calculations a little bit easier, I'm also going to define the base and the height of this rectangle. So I'm going to say that the base is going to be 2a and the height of it is going to be 2b, where a and b are just constants that you guys can pick whatever you guys may choose. Now, since we are dealing with a linear quadrilateral element, as you guys may have guessed, we are going to use a linear approximation function. And remember that when we talked about triangular elements, I said that the number of a coefficients that you have in your approximation is directly proportional to the number of nodes of the element. So for this particular case, if we have 4 nodes, we are allowed to have 4 a coefficients. The reason for this is because the a coefficients are later related to the shape functions, and each node has a specific shape function. So if we're doing a linear approximation and we have 4 nodes, well, our linear approximation for this element is going to be a0 plus a1 times x1 plus a2 times x2 plus a3 x1 x2. Not too bad. And that's going to be for the horizontal component. If I'm looking at the vertical component v, well, it's going to be b0 plus b1 times x1 plus b2 times x2 plus b3 times x1 times x2. So it's the exact same thing. All I did was I switched the a coefficients to b coefficients. So nice and easy. But remember that we said that when we're dealing with these type of elements, or if we're looking at the finite element method in general, well, we're not trying to find a displacement approximation for the entire element. We are concerned with those nodal displacements. So what we're going to do is we're going to take our approximation function that we have above, and we want to express it in terms of 2 things. The first is the nodal displacements, ui and vi, as well as the shape functions, ni. And the shape functions we are going to discuss in the next slide. So what we're going to do is we're going to take the situation we have on the left, And we are going to now convert it to the situation we have on the right, where instead of looking at the general displacement of the element, I am now looking at the displacements at the nodes of the element. So at node 1 there, I'm looking at the displacements u1, which is my horizontal displacement, as well as v1, which is my vertical displacement. If I look at node 2, I'm looking at displacement u2, which is my horizontal displacement, and v2, which is my vertical displacement, and so on for each one of these nodes. So it's pretty easy to see that each node has 2 degrees of freedom, and as such we can rewrite our approximation function to the following, where instead of a bunch of a and b coefficients, we now have u1 times n1 plus u2 times n2 plus u3 times n3 plus u4 times n4, so basically our horizontal nodal displacements multiplied by the shape functions, and the same thing for the vertical direction, but instead of u1, u2, u3, we now have v1, v2, v3, etc. So the question becomes, all right, well, I know that u1 and u2 and u3 and v1, v2, and v3 are going to be those nodal displacements. What exactly is n1, n2, n3, and n4? Well, those are going to be called our shape functions. How do we determine these? Well, we're actually going to use the same process we used for one-dimensional elements. If you guys are saying, you know what, Clayton, I didn't look at the video for one-dimensional elements, and frankly, I don't care about one-dimensional elements, well, don't worry. I will include a video in the description down below showing how exactly we can obtain these shape functions for all of the solid element types that we have covered thus far. But it's actually a pretty simple process. If we take our element and we are looking to find a particular shape function, what happens is we follow 2 simple rules. If I'm looking at a shape function for node 1, so in this case n1, well, the shape function has to have a value of 1 at that particular node. So in this case, since we're dealing with n1, it has to have a value of 1 at node 1. And the other nodes, so node 2, node 3, node 4, they have to have a value of 0. So a shape function for this particular node would look something like this, where it has a value of 1 at node 1 and a value of 0 at the other nodes. And as we can see, this creates a plane. Now this plane is actually described by the following equation, where we have b minus x2 multiplied by a minus x1 and then divided by 4ab. And that's, again, just the shape function for node 1. If we were to move on to node 2, we're going to use the exact same process, where since we're dealing with node 2, our shape function must have a value of 1 at node 2 and a value of 0 at the other nodes. And the plane that describes this behavior would have the following equation. As we can see, it's very similar to node 1, and we can do this for the remainder of the nodes. So looking at node 3, again, has to have a value of 1 at node 3, a value of 0 at the other nodes. We can find our equation. And then finally, n4, same procedure. We're going to have a value of 1 at node 4 and a value of 0 at the other nodes. We can get the following equation. And this is really nice because those shape functions were actually the key to everything else we need to solve. The only unknown that we really had were those shape functions. So using those shape functions, we can create the first thing that we need, which is our shape function matrix. And this is the more simplistic of the 2 matrices that we use our shape functions to define. So as we can see here, it looks kind of complicated, but it's actually really simple in the fact that every 2 columns is just related to a shape function. I look at the first 2 columns, well, it's just n1, 0, 0, and n1. Nice and easy. I look at the next 2 columns, well, then it's n2, 0, 0, and n2. And the process repeats. And this is, again, one of the major benefits of the finite element method in the fact that it's very repetitive. If I had additional shape functions, well, I just keep adding columns to this n matrix. Now keep in mind that if we had a 3-dimensional element, remember, we're still in 2D for right now, but if I had a 3-dimensional element, we actually have a 3rd row which deals with that 3rd direction. So the reason why we have 2 rows in this particular n matrix is because we are dealing with 2 dimensions. The first row essentially deals with the horizontal direction, and the second row essentially deals with the vertical direction. So this one, not too bad. What students start to hate is when we calculate the second matrix that we need, which we call the B matrix. And this matrix relates the strains to the nodal displacement. So this one's going to be very meaningful later on. Now again, looks really gross, but it's actually rather simple because it follows the same procedure as the n matrix above. Every 2 columns correspond to a particular shape function. We look at the first 2 columns here, well, it's all just a function of n1. We look at the next 2 columns, it's all just a function of n2, etc., etc. So if we had n5, n6, well, all we do is just keep adding on columns. Now, as I said, since this B matrix relates the strains to the nodal displacements, Each row of this matrix actually represents a strain component. So the first row represents the strain component epsilon 1, 1, which is the strain in the horizontal direction. The second row represents the strain epsilon 2, 2, which is the strain in the vertical direction. And that bottom row represents epsilon 1, 2, which is actually the shear strain. Now again, since we're dealing with 2 dimensions, we only have those 3 strain components, hence we have 3 rows in our matrix C. If we were dealing with 3D, well, we know that we actually have 6 strain components, therefore we'd actually have 6 rows in this B matrix. As you guys can imagine, 3D gets a little bit more messy, but it's nice because no matter what you're doing with solid elements, all of the N matrices, the B matrices, doesn't matter if it's 2D or 3D, they all follow the same repetitive behavior. But referring back to our linear quadrilateral elements, our particular B matrix will look something like this. Now, it doesn't look very special, but it's actually very powerful compared to the linear triangular elements that we did in the last video. Remember that for the linear triangular elements, our B matrix was actually constant. That's why we typically call those elements CST elements, or constant strain triangle elements, because the strain is constant throughout the element. Now, if we look at the B matrix here, we see that it's actually a function of x1 and x2, therefore the strain is not constant throughout the element. But what's actually nice is if we look at that first row, which again corresponds to the strain in the horizontal direction, it's actually a function of x2, which means that the horizontal strain varies along the height of the element, which means that we can actually model bending. And with most of the civil applications we deal with involving bending, well, that's actually pretty nice for us. So now that we have the B matrix as well as our N matrix, we can go into our stiffness matrix and say, all right, I know the formula for the stiffness matrix. It's simply B transpose multiplied by C multiplied by B. Well, I know what B is. That's not a problem. The only question is, well, what exactly is C going to be? Well, we said that C actually depends on if plane stress or plane strain is assumed. Remember that C is essentially the constitutive law relating stresses to strains. All right, so it's actually not too bad. So if we assume a constant into the page thickness T, and we use plane strain, so therefore we're picking a particular C that corresponds to plane strain, well, our stiffness matrix can actually be obtained using the following equation. Yes, it's actually this gross, but don't worry. When we deal with the finite element method, we always throw it into a computer, so it's not as bad as it looks. If you guys have to do this by hand, I'm sorry. I don't know who your professor would be, but let me just apologize on their behalf. I'm sorry. No one should have to do this by hand. If we were to look at the specific components, well, we have B transpose, not too bad. We have C, not too bad. And then we finally have B. So although this looks really gross, in a computer programming aspect, all we have to do is define what B is, define what C is, and then basically integrate. It's not too bad at all. And what happens is this results in an 8 by 8 matrix. Now remember, it's actually pretty simple to figure out why it's 8 by 8. We have 4 nodes. Each of those nodes has 2 degrees of freedom. 4 times 2 is 8. Nice and easy. Now, one of the things I want to kind of emphasize again, and I did this a lot throughout the triangular elements, it must have drove you guys crazy, but right now, this is actually a real pain in the ass, and it's not because of the size of B, C, or B transpose. All right, those are gross on their own respects, but again, they're just numbers. It's not too bad. The reason why this is actually gross is because we have to take that 8 by 8 matrix and then do a double integral over it. And that's actually going to take a lot of time. Remember, in the finite element method, computation time is very important to us. It's one of the main reasons why we pick one element type over another. So later on, not in this video, but later on, we're actually going to discuss ways on how we can eliminate that need to perform that double integral. Is there a way where we can solve this stiffness without integrating? Well, spoiler alert, yes there is, and we're going to talk about that in future videos. So I just want you guys to be aware that from a theoretical aspect, this is exactly how we obtain the stiffness, but we've realized, well, this kind of sucks. I don't want to integrate twice. Therefore, we figured out ways to actually make it a lot more smooth and fast. So that's the stiffness matrix. From there, we can move on to our nodal forces, which are a combination of 2 things. Body forces, which we call rho B, and traction vectors, which are Tn. So if we were to look at body forces first, again, these would be things like gravity. All right, so gravity, not too bad. You guys are probably familiar with it. At least I hope you are at this point. So you guys know exactly what's happening with these body forces. And how do we attain them? Well, it's simple. We take N transpose, and again, we defined N on the previous slide. It's not too bad. and we multiply it by rho b. So rho is going to be the density of the material of our element. So if we were dealing with, let's say, steel, it'd be around 8,000 kilograms per meter cubed, something like that. And what b is, that's actually going to be the component of whatever the body force is. So if I was dealing with something like gravity, well, we know gravity acts in the vertical direction and has a magnitude of negative 9.81 meters per second squared. So if I were to actually expand this out, again, I know what n is, I can just substitute it. Rho I can take out because the density of our element is typically constant, and then I'm left with B1 and B2. So again, if I was dealing with gravity, B1 would be 0. We don't have gravity in the horizontal directions, at least not that I'm aware of. And then B2 would be that negative 9.81 component that we typically associate gravity with. Now, the thing to keep in mind when we're dealing with these body forces is this. We're integrating over the volume, and this makes sense because gravity acts over the volume of an object, so our integral for our body forces vector is actually going to be the exact same as the integral of our stiffness matrix. Now, you guys may be saying, all right, Clayton, I get the math. What exactly are we doing here? Well, basically, we're taking our element, which again is just a nice square element, and we're saying that this element actually has a body force acting on it. Let's say that it has gravity acting on this element. Well, the question becomes, how do I implement that gravity component into my system? Because remember, when I'm solving the system, I'm not dealing with the element itself, I'm dealing with the nodal displacements. So what this integral essentially does is it takes those body forces that act over the entirety of the element, and it converts them to equivalent nodal loads. Now, those nodal loads will be used when we solve our system for our nodal displacements. Therefore, we actually take into account the effect of things like gravity. Now, on the other side, we also have traction vectors, and these would be things like a distributed load. Now, the integral for this is actually much more simple. It's still n transpose multiplied by a vector Tn, which is going to be our traction vector, but now we're integrating over a surface. We're not integrating over the volume. So if I were to expand this out, this is going to look something like this. Where T1 and T2, well, those are going to be the components of our distributed load in the horizontal and vertical directions respectively. And again, we are just simply integrating over the surface. So you guys may be saying, Clayton, what exactly are we doing here? Well, it's kind of the same process as before with the body forces. If I have a distributed load acting on my element, we can see that a lot of that load is acting on the side of the element and not the node itself. So what we're going to do is we're taking that distributed load, which again acts over the surface of our element, and we are going to convert it to an equivalent nodal load. That's kind of the name of the game when we deal with the finite element method, where we want all our displacements and all our loads, particularly at the nodes, because then we go to our nice formula, k times u is equal to f. We can solve the system, we are good to go. Now, there is one drawback about these linear quadrilateral elements, and that's expected. Remember when we dealt with triangular linear elements, we said that, well, the drawback is it's constant strain. So if you want to model bending, well, good luck. You're going to have to use a lot of those elements. Well, we have a different drawback in these linear quadrilateral elements, and that is shear locking, or as it's sometimes referred to as parasitic shear. Now, this is particularly associated with these linear quadrilateral elements, and the best way to show you guys is to give you guys an example. Let's say that I have a material. So right here, this blue square, it's not an element, it's simply just a material. And I were to take this material and subject it to end moments to essentially bend the material. Well, of course, that we know that it's going to bend in the behavior where we have that nice curved surface and things behave kind of as we expect it to. Now, the problem is when we look at this bending, the surface is curved. But remember, for our particular element here, we assumed a linear behavior between those nodes. So we actually can't model that curved surface. And what happens is when we subject our element to bending, it actually behaves something like this. And again, the reason why is because we can't incorporate that curved surface into these elements using a linear approximation. What happens is the finite element method thinks that this element is actually shearing, and that's what's causing this distortion. Now, what this typically results in is our elements actually being too stiff. So if I were to take a beam in the lab, subject it to some bending, and I get my results, and then I compare it to the finite element method, well, the results in the finite element method are typically going to be stiffer, and the reason why is this shear locking or parasitic shear behavior. Now, the reason why it actually does this is this. In the lab, when I subject something to bending, all of the energy that I'm putting into this beam or whatever it is going directly into bending. 100% of the energy going into bending. However, in the finite element method, because we are shearing, some of that energy that should be going into bending, well, it's actually going into shearing. And that's why we have stiff results, because not all of that energy being applied to the element is going directly into bending. Some of it is going to shearing. Now, of course, this can be avoided by using higher order elements. If we're able to capture that curve along the surface, well, we're actually good to go. So if we were to use, let's say, a quadratic approximation, we can actually capture this behavior and not have to worry too much about shear locking. Another option, of course, is just using a ton of little elements. As you guys have probably seen before, that's typically the solution to most problems, is just increase your mesh size, something like that. But again, it's just something to be aware of. Triangular elements have the drawback of constant strain. Linear quadrilateral elements have the drawback of this shear locking or parasitic shear. Now let's move on to quadratic quadrilateral elements. And every time I say that, I'm going to have to slow down, or else it's going to sound like I'm starting to speak a different language. Now, these quadratic quadrilateral elements are going to look something just like this. So again, we're still dealing with basically a rectangular element. The only real thing that we did is we introduced 4 additional nodes located at the midspan of each of the surfaces. So we went from 4 nodes now to 8 nodes. Now again, for the simplicity of the calculations, I'm going to say that the base is 2a and the height of the element is 2b. As we're dealing with a quadratic quadrilateral element, our approximation is actually going to be quadratic in nature. So instead of a naught, a1 times x1 plus a2 times x2 plus a3 times x1 times x2, well, we add an additional 4 terms, and they are a4 times x1 squared, a5 times x2 squared, a6 times x1 times x2 squared, and a7 times x1 squared x2. So of course, if you guys are doing the finite element method by hand, this is going to get real ugly real fast. I feel really sorry for you if that's the case. What's nice about the finite element method is we just throw this into a computer, so it's not too bad. Now the problem with this is, again, this is still just a general approximation function for the entirety of the element, but I don't want that. I want the approximation function to be in terms of the nodal displacements as well as our shape function. So we have 8 nodes here. Each node has 2 degrees of freedom. Therefore, we can write our approximation function in terms of our nodal displacements, u1, u2, etc., v1, v2, etc., as well as our shape functions, n1, n2, n3, n4, n5, etc. Now remember that the number of shape functions that we have is proportional to the number of nodes we have on our element. So since we have 8 nodes, we actually have 8 shape functions. So if we were to look at this equation, well, the nodal displacements u1, u2, u3, v1, v2, v3, etc., those are what we're trying to solve for. So we really need to figure out what those shape functions are before we proceed. Now what's nice is we can use the exact same procedure as before. So again, we've basically followed 2 rules, which is going to be this. If I'm dealing with the shape function at a particular node, it has to have a value of 1 at that node and a value of 0 at all of the remaining nodes. So if I'm dealing with the shape function here n8, so at node 8, well, the shape function has to have a value of 1 at node 8 and a value of 0 at the other nodes. So the plane that would describe this behavior is going to look something like this. Of course, it's going to be really ugly. Now, you guys may think that the ugliness stops there. Well, it doesn't, because remember, this is just one of the nodes, but we have a shape function for each node. So if I were to go and repeat this process, I'm going to get something like this for all 8 of my nodes. It looks really, really gross. Now, what I can do is I can make this look even more gross by saying that, well, I'm going to take these shape functions and then find my B matrix for the element. This is one thing that I always keep trying to tell you guys, and I'm hoping that you guys listen to me. This may look gross, but it's actually not too bad because it's always repetitive. This B matrix here, the first 2 columns, they're all associated with their shape function n1. The next 2 columns, well, they're all associated with their shape function n2. The next 2 columns, all associated with n3. And the same process repeats itself. So it doesn't matter how many shape functions we actually have. All we have to do is just keep adding on columns to this B matrix. Nice and easy. Now that we know our N matrix as well as our B matrix, we can go on to our stiffness matrix and nodal forces and say, all right, I know everything I need to know. I have a nice formula for my stiffness matrix where it's B transpose times C times B, then integrated over the element. And I said, well, I now know what B is. C, well, that depends on if I pick plane stress or plane strain. All I need to do is substitute everything in, integrate over the element, and I'm left with the 16 by 16 matrix. Moving on to the nodal forces, same thing. It's the exact same process as the linear element. The only difference is now my B matrix as well as my N matrix have changed. All I do is account for that change. I'm still good to go. So if I were to solve my nodal forces, it would result in a 16 component vector. Now, the general rule of thumb here is the complexity of these calculations is proportional to the degree of freedom of the element. So notice how I'm saying element here. So the degrees of freedom of the nodes in 2D are always 2. We have a horizontal direction as well as a vertical direction. But the element itself has to take into account the fact that we don't just have one node, we have many nodes. So for example, the quadrilateral element we just discussed, it has 8 nodes, and each node has 2 degrees of freedom. Therefore, the element actually has 16 degrees of freedom. And as such, the stiffness matrix is 16 by 16. Now, the thing that we have to keep in mind that we're still dealing with two-dimensional elements. We have a 16 by 16 matrix for one two-dimensional element. Now, of course, when we're dealing with the actual finite element method and we're modeling our real-life applications, we typically have hundreds, if not thousands of elements. And each one of those elements is 16 by 16. So this is kind of alluding to the fact that I discussed before. I don't want to be integrating those stiffness matrices. It'll take too long. You guys will be sitting there forever. You guys have better things to do with your life than to be integrating stiffness matrices. So later on, we're going to discuss, all right, how can I eliminate the need for that integration? Now, to wrap it up, we're going to take a look at 3D quadrilateral elements. So the 3D version of the quadrilateral element is typically referred to as the brick element. Why? Well, because it looks like a brick. So of course we have a linear brick element, which is basically a brick with a node located at each one of the corners of the brick. So of course we're going to have 8 nodes, one for each corner, but one of the major differences now is that each one of those nodes has 3 degrees of freedom. Remember that when we're dealing with the 2D case, 2 degrees of freedom, horizontal direction as well as the vertical direction. But now in 3D, we have that third direction, that into the page direction, and we actually have to account for that. So our stiffness matrix in this particular case is going to be 8 times 3, which is going to be 24 by 24, because this element itself has 24 degrees of freedom. Now that's just the linear brick element. When we go to the big boy, which is the quadratic brick element, we add those additional nodes at the midspan of each one of the surfaces. So what happens is in the quadratic brick element, we actually have 20 nodes. And again, since we're dealing with a 3D case, each one of those nodes has 3 degrees of freedom. So one of these brick elements is actually a 60 by 60 stiffness matrix. Really gross. Please don't do this by hand. This is why we have computers. We need to make our lives easier. Now, I'm going to wrap up by saying this. At this point, we discussed what our general solid elements are, we discussed triangular elements, and now we've discussed quadrilateral elements. Although they seem different, it's actually the exact same process, which is why triangular elements, quadrilateral elements, brick elements, etc. all fall under the solid elements category because the process for them is exactly the same. The equations for the stiffness matrix and the nodal forces are exactly the same. The only difference between these are the shape functions. The shape functions depend on both the element type. Am I dealing with triangular elements? Am I dealing with quadrilateral elements? As well as the geometric order. So am I dealing with a linear element or a quadratic element? So what happens is we find the shape functions based on the element type we select. Then with the shape functions, we find the B matrix, which we did for every single element type. And then finally with the B matrix, we can find the stiffness matrix. So again, even though these elements may seem different, they're all the exact same process. The only real difference is going to be those shape functions. But yeah, that's it for quadrilateral elements. I hope I was able to help you guys. If not, then I'm really sorry for wasting your time. It's not what I try and do, but you guys are smarter than me. So typically, I may be wasting your time. And if that's the case, I am sorry. So thank you guys so much for listening. I really appreciate it. I will see you guys in the next lecture video.